Okay, is it on? Yeah. Um, okay, I think I'll get started. So, my name is Grzegorz Kołodziejczyk. I'm the CTO at Ragnarsson, and we're a Ruby software development company. And today, I wanted to talk with you about working with binary data in Ruby. So maybe a quick show of hands. Does anyone do any work with binary data? Cool. One person. Two people. Great. More than I expected. So this talk is going to be a bit code heavy compared to the rest. So like if you don't see a screen so well, you might want to move or I don't know, get some glasses or something. The plan for the talk is first I'll give a quick intro of how we got into this. Then we will go to like binary data one-on-one so that everyone has the same basic level of understanding. Then I would like to go through what's available in the Ruby standard library and how we can use this. And then I'd like to talk about a gem that made it everything like super easy compared to the standard library. Okay, so how we got into this. So we are a software house, so we deal with a wide range of different subjects for our customers. But those apps are mostly similar on the technology side, right? So the business logic varies from project to project, but the tech side is mostly the same. You have a database, you have to have some web views, you do some processing in the background, and that's pretty much it. Like the vast majority of the projects that the clients want to work with us on, they look like this. So about 2.5 years ago, we finally found the Holy Grail. We had a client with a project that was definitely not a cookie cutter project. It was very different from everything else. And the project is about collecting data from meters and sensors. So those could be like all the meters that you have in your apartment are getting digitalized. So the heat meters, the water meters, smoke detectors, heat cost allocators, they are all getting digitalized. And the reason is that like there is regulation coming in that will make it so that the utility companies have to do the readouts every month instead of every year, and this changes the calculations, and you can't do this manually anymore, so you have to digitalize. So those meters, they send data using a custom protocol. We collect this with gateways. Those are just Linux boxes running on site. And those gateways send the data over MQTT. Then we ingest the MQTT data with like a simple Ruby worker and put everything that's coming in into various sidekick queues. And the data that comes in is in a protocol called OMS. It's like Open Metering Specification or something like that. It's a European norm, so like those EN dash a few digits standards that you can see on pretty much everything in Europe. It's one of those norms. But it's been worked on since like the early 90s, and the work was done by just putting layers on top of layers on top of layers. So it's kind of complicated at this point right now. So we're running this in production for over 2 years now. It's running fully on a Ruby stack. We do about 2,000 requests per minute. So requests in this case are those like messages coming in over MQTT. And using Ruby allowed us to be industry leaders in the amount of supported devices, which I'll come back to this later. So when we started it, like when the client approached us, the first thought that we had was like, it's a low-level protocol, you have to do it in C, right? Everything that's like low-level is in C. We're gonna be able to find much more like libraries. Someone has to be working on this, and maybe they publish something. So that went nowhere. There are no libraries. It's a very niche protocol. And then we started thinking, do we really want to write C? We don't have much experience writing C. Last time I did it was at university, which was a long time ago. So we started thinking, can we do this in Ruby instead? And the answer is yes, that we could. But before I show you how, we have to go into sort of like binary data one-on-one and give everyone a brief explanation of what we are working with. So the first thing that's obvious to point out is that all data is binary. I mean all data that's processed by computers. But to say that is to say like all keyboards are mechanical keyboards. Technically it's true, but if you point this out, you're kind of a jerk. So with that said, a bit is either 1 or 0. It's a smallest unit of information. A byte is a group of 8 bits, and this is like the basic unit that everything is based on. And does this look familiar to everyone? Like if you took any computer science courses, then yes. If not, then probably no. So you have 8 bits, and looking from the right side to the left, you have the least significant bit, and on the right you have the most significant bit, and they are assigned different values. So those are 2 to consecutive powers, and if the bit is 1, it means that we store this value, right? So if we have a byte consisting of 0, 1, 0, 1, 1, 0, 0, 1, it means that we have 0 times 128, 1 times 64, 0 times 32, 1 times 16, 1 times 8, 0 times 4, 0 times 2, so it sums, and 1 times 1, so it sums up to 89. Does this work for everyone? Like, cool? Yeah, good. Endianness is byte order. So with bits, we know that like as they arrived over in the memory or over the network, we read them this way. But if we have bigger numbers that won't fit into like 0 to 255 that would fit into a byte, we have to deal with the byte order. So let's say you have a 4-byte integer. So you have those bytes coming in, and you can have it either be big endian or little endian. So does the most significant byte come first or last? It's not really relevant to this, but it's kind of good to know. ASCII is for character encoding, so it stands for American Standard Code for Information Exchange, and it's basically a big table of mapping of a byte to character. So for example, if you in Ruby have this character A, and you call this ORD method on it, you will get the ASCII mapping for it. So 97 in ASCII means A. To go the other way, you can go from like 122. You do this method.chr, short for character, and then you get the character back. And so the characters that are encoded are printable and non-printable, sort of. So this goes back way to like actual printers. But there are like special characters, like 10 is a new line. There's like the carriage return, and so on. Another thing that we need to know is the hexadecimal notation. So to write down, like to have a readable representation of the data, it's convenient to have it in like a short form. So instead of having like this long string of bits, which is unreadable, we transform them into like base 16 encoding. So for example, the number that we had before, 89, in hexadecimal is 59. So it's 5 times 16 to the power of 1 and 9 times 16 to the power of 0. And they start like 0 to 9 are the same, and then the digits 10 to 15 are assigned letters A to F. So A is 10, B is 11, and so on. Okay, so we learned about bits, bytes, endianness, ASCII encoding, and hex. And that's basically everything that we need to know about it for now. Okay, so now we can take a look at what's available in the standard library. So you have those two basic methods, string pack and string unpack. Did anyone ever had a chance to use those? Okay, cool. So there are uses for it. The basic thing that we can do is to take the binary string that we have with like garbage inside it and unpack it to a hexadecimal representation. So for every byte, you will have 2 characters that represent that byte. And the shorthand for that is H star, which means like take everything and treat it as hexadecimal notation. Unpack returns an array of objects in Ruby, but there's also a shorthand if you know that you only take, if you only want to take one thing, you can unpack one. And then we can go the other way. So if we have a string with the hexadecimal representation, we can pack it into a string with just the binary data. The reason we used hexadecimal representation instead of just like printing it out with like the way Ruby prints out strings is that Ruby tries to interpret them as much as possible as like readable text. So if you match a character from the ASCII table, it will show the matching characters, like 420A in hex is capital B and a new line. Also, if like you have a byte sequence that looks like Unicode, Ruby will try to show the Unicode character. So that can be confusing. That's why if you want to look at the data that comes in a readable way, it's better to have it in hex. String pack and string unpack have a lot of options, but for now we can take a look at a few of those. So the ones that we can use are decoding unsigned integers. That's very common. So depending on the size, so 1 bit is C, 1 byte is C, 2 bytes is S, 3 bytes is L, 4 bytes is L, and 8 bytes is Q. Then we can have decoding binary strings into various representations. So, for example, we used H, which is a hex string with high nibble first, which is like the nibble is half a byte, so it decides on the order of the characters. But also useful is like a bit string. So if you have a byte and you want to show the order of the bits in it, then you can use capital B. And also capital Z is for null terminated strings. That's also sometimes useful. So now let's go to some examples how we can use this. So an IP address is a very common data structure that we use all the time. So an IP address in itself is a 32-bit number. But if we treated them as numbers, they would be just unrecognizable to anyone and very hard to not make any mistakes with. So they are typically represented by 4 smaller numbers delimited by dots, right? So you take the 32 bits, you divide them into groups of 8 bits, and take them, like, translate them into normal decimal numbers. So let's see how we could do this conversion in Ruby. So we have a binary string that includes an IP address, right? And to get it into a readable format, we can unpack it. So from the table before, we saw that C is a 1 byte unsigned integer. So if we tell it to unpack into a sequence of 4 1-byte integers, it will take every byte, transform it into an integer, return an array. And then if we join the array with a dot, we get this nice readable representation. To do it the other way around, we can use pack. So first we have to split the string. We map every part of the string into an integer, right? Then those integers can be packed into one long representation, and we get to the same part, to the same place as we were at the start. So next we have MAC addresses. MAC addresses are like unique identifiers of network interface controllers. So basically anything that's connected to any network has to have a MAC address, and it's good if they're unique. And they are represented by 6 octets in hex, delimited by colon. So what it means is you have an octet is like 8 bits, so it's a byte. It's another name for a byte. So they look like this, right, in the serialized way. So if we want to unpack them by like this hex delimited format, it looks a bit different. So we have a sequence of 6 H2. So H2 means it's a hex. It's to get it in a hexadecimal format, and take 2 characters for one section. So we have 6 sections of 2 characters, and we join them with the colon, and we get a nice string that's readable to a human being. And then the other way around, we can split the string and pack it the same way, and we get back to the binary representation. So that's the extremely simple example that we could do. For something that could be more practical, we could look at gzip and extract the original file name for it. So it's kind of an artificial use case, but a lot of times you have like web forms where user can upload files. And for example, you only want to take images, but you don't trust them to only provide images, right? Because they could change like an executable and rename it to a JPEG file and upload it, and things will get weird. So sometimes you want to verify that the file is in the format that the user says it is. So here it's like an artificial use case, but let's say we want to extract the original file name for the gzip to see if it was renamed or not. So if we had this task, we would start by looking at the RFC for gzip. So I'm gonna break it down into smaller parts and look at the format of the file. So a gzip file starts with a header. The header has first 2 bytes called ID1 and ID2, and those are like a magic value that verifies that it's gzip. It has to be this value, and otherwise you can like reject the file and it's not this. So we can use this for verification. Then you have this 1 byte telling you what's the compression method, and there's only one compression method, but there's a flag for it. Then you have 1 byte with flags. Sorry. Wait. Then you have 1 byte with flags. This 1 byte tells you what other things are there in the header. And then you have the modification time, some other flags, and the operating system that was used to create the file. So depending on the flag, like 1 bit in the flag byte, you can potentially have an extra field that starts with like 2 bytes of xlen, and then for this length you read out the extra bytes. And eventually you have the original file name 0 terminated, which is what we want to extract, right? So now it's the code part. So let's try to write a method that will extract the file name for this file. So we open the file. we read the 10 bytes that we are sure that will be in there in the header. We unpack it with like this magic string of H4, H2, B8, L, H2C. So we have H4 and H2 are those hex strings. B is a bit string, so we can take 8 individual bits. Then we have L, which is unsigned int 32, and then H2 again, and C is unsigned int of 8 bits, right? Then we have those magic values, right? So if the header doesn't start with 1F8P in hex, it's not a gzip file, we can drop it. If the compression method is not 08, it's something weird, so we can also drop it because there's only one supported compression method so far. And then we take the flag, and the flag is like a sequence of 1 and 0s, so we can split it and take those single values. And then like if the flag for extra is set to 1, we have to read out the length, take out one value, which is the unsigned int of 2 bytes to read the length, and we have to seek the file to move the head forward, right? And then finally we can read out the file name and unpack it as a 0 terminated string, right? And that's pretty much it. So if we run it, it works, right? If we rename a file, then it shows up the original file name. But this code looks like crap. It's very hard to read. It's extremely hard to code review. And if you have code like this, especially with those like long strings in unpack or pack, it's a bit like regex, where like if you have a regex that's long enough, it starts to be write only because you can't read it and process it in your mind. You just can, it's easier to just figure out what it has to do and write it from scratch. So very fast we decided that this is no way to go. Like you can't write maintainable code like this. Quick side note, the magic part of the gzip file that I mentioned, it's used in a gem called Mime Magic, and it's a really cool thing. They have like this huge table of all possible data for like binary formats or even not binary formats, but like all file formats, and they can like look at the content, and looking at certain offset, they know what to expect and will tell you if it's this file or not. So for gzip, they have also this this check that it at offset 0 it should start with those 2 bytes, and like those 2 bytes are exactly what we mentioned. And this is an example why we always use the hexadecimal notation, because Ruby will try to interpret like there are many ways to interpret a certain sequence of bytes, and for example for this it tried to decode it as Unicode. Okay, so that was not a good way, but there is a better way that we eventually came to use, and it's a gem called bin data. You can find it on GitHub, and it provides a declarative way to read and write structured binary data. So not only does it like makes reading things out simpler, but it also gives you tools to easily build those objects and then serialize them into binary, like by not adding too much code. For stats, it's used by like 1,300 repos, so it's reasonably popular. It's not like some niche thing. So now we can go back to our original problem that we had. So the IP address is a sequence of 8 bytes, right? And if we write a bin data structure for it, it looks much nicer. First of all, it looks like Ruby, like good Ruby that would pass code review. So the way this works is first we define how the data is structured. So in this case, it's an array of an array of octets, which are of type unsigned int 8, so an integer that fits in 1 byte, and initial length of 4, and that's for writing those. And then we have setters and getters, which tell the library how to transform the data into like a readable representation, or a representation that we can use further in like the data processing pipeline. So, for example, if you want to serialize an IP address, we build a new object, and there's a method to binary string, which returns the same string that we had in the first example. Sorry. So we can also read the binary string and get the readable string out. It looks pretty much the same for MAC address. So we have an array of 6 octets, and they're unsigned int 8 as well. And then we split the value and map it to integers. And if we want to get it, we map the octets into like a hexadecimal representation. So it works the same way. Reasonably simple example, so doesn't it's not it wasn't that bad either in the first version, but this one is nicer to read. But compared to the extraction of file name from gzip, this is a much easier way to approach this problem, right? So instead of this like procedural code to go through step by step what has to be where and read it out, and then like seek the read head in the file and so on, we have a declarative way to just describe what it is, and the library takes care of like reading and transforming all the things. So the things that we could compare here is line 7 and 8 are the assertions, same as line 6 and 7 in the method. So in addition to telling what to read out, we also can set an asserted value of this magic string, and if it's not there, we just drop it. We have the 1 byte with all the flags already split up into separate fields, so it's easy to read them out. And then we have the only if proc, which tells the library like the condition where it should go into this block or this field. So it's easy to skip the extra field if the flag is not set. And then the 0 terminus string is just string z. So this, when we discovered this and played with this, we finally understood that, okay, this is at the point where we can actually use Ruby to write code that parses this data. And this is something that we can work with and maintain and do code review on, and it won't be like unbearable a few years from now. So in the end, I wanted to give you a few examples of like real life usage, because the examples before were just like made up for this presentation to have something easy to parse. So for example, the meters that we read out often store values in BCD. Does anyone know what BCD is? It's binary coded digits. It's a weird format that like stores a number with digits in a separate half byte. And the reason they do this probably is that it's very easy to wire up this to like a segmented LCD display. So probably for legacy reasons, they just use the data structure that they had in the firmware for those meters anyway. So here we take those. We have a setter and a getter, and we just multiply by the powers of 10 to get the actual value. Another example that we have, the protocol for OMS defines this data information field. And the interesting part here is that you have the first bit of this field is like an extension bit. And then at the end, you have a data information field extension if this extension bit was set to 1. And this extension also has an extension bit. And this extension also can be can have another extension. So you have a potential for like infinite recursion. So with bin data, we can just write it like this, and it works for any amount of extensions. But like, try to imagine what we would have to go through to read something like this out by using just string pack and unpack, right? And then my favorite part of this protocol probably is this lovely data structure. It's a way to store like a very reasonably precise timestamp up to a second in 48 bits. And I had to, like, when I started implementing this, I had to like do some coloring to have a mapping of like what is where. So like it starts pretty okay. Like you have the second, minute, hour, and day that are in a reasonable way. But then the year is like half of it is in one byte and the other half is in the other byte. I don't know, like probably someone had a very good reason to do this way. But like I wouldn't really want to use string unpack to parse something like this. So that's why we use bin data, and it's actually not that bad, right? So even though the structure looks very convoluted, you have to just declaratively go through it, write down every single bit, which part it belongs to, and the only tricky part is that we had to like convert the year, and of course like it's like an offset from year 2000 to save 1 bit, but whatever. It's usable, right? We use it, it works, and it wasn't actually that bad to write. Another example is that a lot of fields in this protocol have like same as in gzip, you have 1 byte with like feature flags, sort of, and then the rest of the structure depends on if a certain bit in the previous flag was set, right? So we extensively used only if flag. Okay, so to recap, we were thinking if actually approaching a problem like this is doable in Ruby. It's definitely doable in Ruby. It's been running, we haven't ran into any limits caused by Ruby in 2 years, over 2 years running it in production. It's quite fun to work with. For some definitions of fun, but like I like it, I enjoy it. And because it's in Ruby, it's much easier for us to react to like weird quirks of the protocol, because like the default specification is something that was started in the 90s, and people were like adding more and more features on top of other features and adding like different flags, and like if you have this combination of flags, you have this weird thing, and then all the manufacturers, like the people that implement this, all get lost in the specification and like mishandle the implementation in their very own special way. And because we use Ruby, we can do a lot of flexible stuff. So like we can take a look at it one level higher and just do like Ruby code to fix those. For simple operations, pack and unpack is pretty good. Like if you just want to transform like a binary string into hex, that's great. That's useful like for encryption and so on. Like if you have a encryption key, you need to have it in a binary format. You just like pack it into a binary string. But for like more complicated use cases, bin data just saved our lives. Like we couldn't do this without this gem. As a bonus point, so we were kind of worried that we were going to be like processing stuff on Ruby and it's going to be slow. And this is a screenshot of AppSignal, of the action that's doing the processing, like at the very start of like when you ingest the data into the system. And can you guess which part is doing the parsing of the binary data? It's this one. So like it's negligible compared to like doing one database read in the same action. So the only thing it stands out with is the number of allocations because it's doing a lot. So this is it. I think I caught up to the schedule. If you have any questions, I'll be here around, so just come up and we can talk. If you're interested in this kind of work, you can work with me if this is something that you would like to do. Yeah, thanks.